Okay, I think we're live. All right. So let me quickly summarize our project, the project that we're working on. So the name of the project is Parasitic C, and it is a eventually it will be a C compiler written in C that parses C code and outputs C code as well. And the reason I'm doing this is so that once we have that compiler working, then I can very easily make it self-hosted and then begin to evolve the source language into its own language, which is not C, because C is kind of an annoying language to work in. It's more fun to design your own language. So, but I also want to learn how to bootstrap a compiler, so this is the approach I'm taking. So that's why it's called Parasitic C. It's going to sort of eat C from the inside out. But first we have to parse the C language. So that's what we're working on today. I am continuing work on the parser. We're using a recursive descent parser. Here is a Wikipedia article on recursive descent parsers. The grammar for a recursive descent parser has to be I forget what it's actually called, but it can't have left recursion, and it should not have ambiguities. And previously, I believe in the last video I made, I showed how I was overcoming left recursion when it comes to this postfix expression non-terminal in the grammar. So this is there's a link to this in the description, but this is a grammar, a Yak grammar that somebody has made for the C language, and I was basing the parser off of that. And this postfix expression non-terminal, a primary expression is basically like a variable identifier, a constant like 1, 2, 3, a string literal or parenthesized expression, and then postfix expressions parse this a primary expression directly, or, and this is where the left recursion comes in, there is postfix expressions followed by the array access operator, the dot field access operator. This is plus plus and minus minus. So there was definitely left recursion in this grammar. And in the last video, we figured out how to transform this non-terminal into one that works inside of a recursive descent parser, and by removing the left recursion. And it was a little bit of a process, kind of frustrating. Well, it wasn't too bad, but as I continued after that stream sort of working along, I realized that we're going to come across this same problem in other cases, in a bunch of other cases, and I'd rather just not deal with it. I don't want to have to think about the grammar as much. I'd rather just think about the C code that I'm writing in order to implement the grammar. So for that reason, I found this grammar online, which is a grammar for the C language, and it is a grammar. It is a parsing expression grammar. So this is the Wikipedia article for that, parsing expression grammars, or PEGs. And the nice thing about PEG grammars, or PEGs, parsing expression grammars, is they work a lot better for, they don't have left recursion, and they make a lot more sense if you're trying to implement a recursive descent parser. So since I found this peg grammar, I thought, all right, let me just use this to as a skeleton, the instructions for my language, for my parser. So I copied it over here into the project. I need to make this bigger, and let's move this to the side. This peg grammar was created by this person, Roman R. Redzijowski. I can't pronounce that very well. And so thank you to them, and the link to that grammar is in the description if you'd like to look at it or modify it or anything. And I'd like to show you postfix expression. So if you ignore this line right here, this is exactly what we came up with previously in order to parse a postfix expression. So if we look at postfix expression in the Yak grammar, there's all this left recursion here, but we figured out that effectively it means first parse a primary expression, and then parse 0 or more of these things, which is left bracket expression, so this is the array index operator, left parenthesis, this is function call syntax, a dot and then an identifier, that's field access, and then the pointer, that's the double arrow operator, or this arrow operator. Okay, so the nice thing about parsing expression grammars is they've already done this work for us of removing the left recursion and telling us where we need to do iteration. So the star down here means iterate. So that's great. And what I did was I completely restructured the parse.h file to use, I just copied this entire grammar over, put it in comments, and then we have all the rules in comments, and I began filling out sort of the basic, all right, I just started, putting the things that we already have where they're supposed to be, renaming a couple things, structuring it according to this grammar. So I almost have like a to-do list now of things I have to implement. So for instance, I've parsed a pound include. I have code for parsing pound include directives, but I still have to write a function for declaration specifiers, whatever that is. And if we go down to most of the work that we've done so far is with expressions. So here's primary expression, and there really is like kind of a one-to-one correspondence between the structure of this specification, the grammar specification, and the code that we have to write. So string literal, parser accept, or lexer accept literal string, and then create the expression node, parsing constants, so it reads very, very nicely, which I appreciate. Okay, so let's see what we need to work on. I should also point out that anytime we see L wing and R wing in the grammar, that is what the person who wrote the grammar is calling the curly braces. So R wing is just that curly brace. L wing is the opening curly brace. So let's work on parsing the function call syntax. So in order to parse a function call, we need left parenthesis, right parenthesis, and in between an argument list, optionally. So I'm not sure how I want to deal with optionality. I haven't come across this yet in implementing stuff. So I think I can just use a while loop, and like if it doesn't parse anything, we just skip it. Let's try it. So I want to put it right after the array index expression function call. So we need if lexer accept lxr token open paren and arglist equals, this is a function I have not written yet, parse argument expression list. Argument, oh, I have a, but I do have a stub. Okay, that's nice. This needs extra parentheses around it because it's an assignment. And lexer accept, and actually we should have expect. This is interesting. Let's continue though. Close paren. Okay, so let's call, do I have like a not implemented thing yet? Really, I'm not doing this in a great order. I think what I should be doing is adding a test first. So where are my tests for expression? Parse expression. And I guess I could do it here. Let's just test this in isolation. So my func 1, 2, 3. And display it. Okay, so that's our test. If we run the program right now, yes, we haven't declared this identifier. So I really wish we could, I guess what I could be doing is putting this inside of a block, but it's not a huge deal. Struct expert pointer arglist. Implicit function declaration, parse argument expression list. So that's because it's defined below this function, so we need to add it to our forward declarations. I'm just putting all of them up here. Struct expr pointer parse. Let's just copy this, and we need parse argument expression list. Yeah. Okay, and we have a not implemented. So if I go here, parse argument expression list. All right, let's implement this. So first we need to parse an assignment expression. Struct expr pointer expr and okay, this is assuming that we have at least one assignment at least one argument passed to the function. So let's just follow the grammar, and which means I need to up here also accept an empty function call, 0 arg function call, and that's going to be very similar. Let's quickly do that. not be an argument list. I believe this needs to be below function call though, because this is smaller than that. So if parse argument expression list fails and and there's nothing inside, then we want to skip this and go to here. Okay. And I think, okay, I'm not being very structured about this, but I think I should define the data structure quickly. So where is struct expr? How do I search for this? Here we go. Well, we found it. Expr, it's a call expression, and we need to add a variant to our union, struct so this will be the callable, and then we need the arguments. So I think I might just be able to, I think I need a new struct here, which is essentially like a linked list. Arg list pointer args. Okay, and we'll call this a call expression. Let's define arglist, struct arglist, and this will just be kind of a linked list. So a linked list has data, struct expression pointer, expr, and it has a next pointer, struct arglist pointer next. Okay. And I think I should move this down below here. And I'd like to give it its own display function as well. Display int display arglist. Given a file pointer out and a struct arg list pointer list. We need to say if list is null, then we can we don't have to print anything out. So maybe we will just say if list is non-null, then display expression to the outstream, and which expression is it going to be? It's going to be list arrow expr. Okay. And then we want, let me write it recursively first, and maybe we can just leave it recursive. Fprintf s to the out stream, we want a comma and a space. Maybe we want a comma and a space. So we want to say, oh boy. Okay, so if list is non-null and list arrow next is non-null, then we know we can print out a comma. And then we want to display arglist to the output stream with list arrow next. Okay. Else if list is not null, then we need to, then this means, I guess I could check again, and list arrow next equals null. Then we need to just print out the final element, which is return display expression to out list arrow expression, and then we're done. And otherwise we just return we should return an integer. What is return 0? Like I guess that makes sense. We're not printing anything, and fprintf. Oh, good lord. I don't remember what fprintf returns. Let's look it up. Okay, fprintf. Return value. Okay, which function are we using? We're using fprintf-s, which is number 6. Return value for 5 and 6, number of characters transmitted to the output stream, or a negative value if there's a runtime error. Okay, or if there's an error. Okay, so yeah, I should return 0. Okay. So that should display an arg list. All right. Now, are we done up here? Yes, we have a call expression which has an arg list and a callable. Yeah. Okay. So now let's go back down here to here, and we will allocate. Okay, so the way I'm doing this, because it's in a loop, we need to allocate to a new expression, and then expr is the previously built up expression from the previous loop body. So we say new expr arrow tag equals expr call expression. Then we need to say new expression arrow as call. The args is going to be equal to arg list, and new expr arrow as call dot. The callable is going to be the previously parsed expression. And then this was successful, so we need to set expr to be new expr and continue the loop. Okay. And I think it might be worth it to break this up a little bit. I don't know. I like how this reads. Yeah, we'll keep it like this. I think it's a little bit less efficient, but that's okay. All right. So instead of an arg list, the args are going to be null in this case, and then everything continues as usual. Okay, so now we need to actually parse an argument list. So we're down here, parse argument expression list. So first we need to parse an assignment expression. Expr, and we'll say if you can't parse this, return null. If you can't parse this, return null. In fact, maybe that's all we need to do. Because null is a valid arg list. Oh, this is not going to be an expression. This is going to be an arg list pointer. Okay, so try to parse an assignment, parse assignment expression with the lexer. If you can't, then we can return null, and this is a struct arg list pointer. Okay, and it says, hey, we parsed the empty list. Okay, so actually, up here, we're asking it to parse an argument expression list. But we're requiring that it return a non-null value. Okay, so the way to solve this is actually we do this, comma true. The problem with that is I then have to implement the comma operator for expressions, and I really don't want to. So I think we'll just keep it as it is. And if this returns null, fine, we break out and then we continue here. Is that actually going to work though? Because we've already accepted an open parenthesis. No, that's not going to work. Okay, so we do need to restructure this, our approach here. So unfortunately, we need to do it like this. First, we accept the open parenthesis. Then inside, we need to say okay, and this actually solves this problem as well. So we have arg list, and we can immediately say parse argument expression list with lexer. And then we need to say expect if this is not the case, that we can't lexer expect a token close paren, then we need to return null. Okay, but now we have parsed something, and we know that arg list is either null or something valid, and either of those is totally okay. So now we can assign arg list to args, and that should work, and now we don't need this at all. Okay, that's nice. All right, so we've either broken out early here if we can't parse an expression list, and then we need to go into a while loop, and we need to say parse 0 or more commas followed by assignment expressions. Okay, 0 or more commas followed by assignment expressions. And this is going to be interesting. I'm worried that I might be parsing these backwards, or we might be printing them backwards. We'll have to see. Let's go through it and we'll figure it out. In the test, it'll show us. So, all right. So we need to parse a comma. So I guess we should say, in fact, we could even say it up here. If keep going while lexer accept token comma. Okay. And then when we get to the bottom, we can say return expression. I think it's a little disingenuous of us to say that we are following this grammar, so I'm going to modify it to say, all right, we could also return empty string. I mean, we could also parse the empty string here. Because it's true, if we can't parse an assignment expression, we're returning null. All right, so inside of this loop, we need to just keep parsing assignment expressions. So struct expr pointer new expression equals parse. I think I should do it like this. So if you get a comma, interesting. Okay. I think I would actually like to allow an optional trailing comma, and I don't want to have to come back to this. So I'd like to do it now. So I think what I'm going to do is say and parse assignment expression with Elixir. What does this mean? Well, you can get both a comma and one of these. I don't remember what my thought was. All right, let's put this down here then. Okay, let's keep it simple. So we do this. I guess we could keep it like this, and then we could have an if condition if expr equals this, or sure. If that's the case, then we need to arglist pointer args. We can say args equals malloc size of star args, and then args arrow expression, so the current expression. Oh, actually we should have allocated up here. So as soon as we get an expression, we have to put it inside of a list somewhere. So args, we need to allocate a new arg list node. We can say the expression equals expression, and args arrow next equals null. Then we go into this loop, and we can say we need a new arg list here. New args. I think this is going to come out backwards, but maybe it doesn't matter. All right. Oh dear, I don't want to have to write a list reverse function in C. I can do it. I think I've done it before. new args equals malloc size of star new args arrow expr equals expr new args arrow next equals null. And then we want to say args arrow next equals oh dear, this is complicated. Why is this so hard? This would not be hard if this was in a language with cons. Oh dear. Args is our arg list. It's a singly linked list. I think we need to hang on to the beginning of the list. And maybe we should also be hanging on to the tail of the list. So arg list, args, and maybe we'll call this first and last. We'll have 2 pointers, first and last. And then here we say first equals size of first. And we also need to initialize last. Last equals first. Then parse an expression. Allocate a new node. And this will be the last. And then we want to say last arrow next equals new args. And finally last equals new args. Continue. And then down here we want break. All right, so we break out if we don't come across any commas when we're expecting to. We also break if we can't parse an assignment expression after parsing a comma. So if you don't get another expression after a comma, we also break and just return not expr but first, a pointer to the first. Okay. This is a little concerning. I think it's done though. Let's see if it works. Alright, we have some errors. Incompatible pointer type. Where are we? Arg list. This is not an expression. This should be a arg list pointer. Parse argument expression list. Yes. Incompatible pointer types again. Arg list, parse argument expression list. Parse argument expression list. Is that because up here we have parse argument expression list and this should be an arg list? Yes. Okay. All right. Implicit declaration, parse assignment expression. Parse assignment expression. Okay, display expr is not implemented for tag expr tag 13. Okay, display expr, yes, so we forgot to tell it how to print case expr call, return display expr, and this is a postfix expression, so postfix plus plus dot field, I think this should actually be up here, which means that this ought to be right after array index, and this, in order to keep things clean, should be after array index as well. Array index. Okay. Display a call. Okay, this is messing everything up. So first we want to display an expression to out, and the expression will be expr arrow as call dot callable. Next we want to fprintf s to out. We want to print open parenthesis, and we're going to want to do the close parenthesis as well. And we need to do display arglist out, and we say expr arrow as call dot args. Put some ands in there. Okay. Let's see if this works. I can't. Yes, I don't need the ampersand at the end there. Display arglist is not defined yet, so we need to add that up here. Int display arglist, and it takes a struct arglist pointer, too many arguments to the function, and it takes a file pointer as well. Okay, 1, 2, 3. So I think it actually worked. Function 1, 2, 3. Let's also test that it works with no arguments. It does not quite work with no arguments. Interesting. Why is that? It's like not printing the last argument. That's very strange. My func. What happens if we do this? That should be an error, right? Yeah, unexpected token got comma, expected close paren, yeah. Okay, so that's good. What happens if I do this? A single expression followed by a comma. That should work, right? Yes, okay. It loses the comma, but that's all right. We do have this problem with, let me try, if I add a postfix expression on here, is that still gonna not print the, it doesn't print anything after here. Does that mean I'm like corrupting memory or something? Where am I displaying an arglist? So if the list is null, we should return 0. Maybe let's restructure this. If the list is null, return 0. We wrote 0 bytes. If list arrow next is null, then we should just display the current expression. If, okay, otherwise, we should call the recursive case. We should do the recursive case. So display the current expression. In fact, we do this in both cases, and this is fine. And then print the comma, and print call arglist with list arrow next. Yeah, I mean, that should be working, right? I'm not seeing where the bug is. But clearly there's a bug here. First we display the callable. Then we print Oh, I see. Oh, that's so weird. Okay. So display arglist is going to return 0. Because we're not printing anything here. Okay, so I should actually be returning 1, even though... Oh my god. Ugh, I hate error handling in C. So really what all of these ought to be, we wrote 0 bytes, but that doesn't indicate an error. So actually, what every single one of these fprintf-s calls should be, if they're going to be in a Boolean conditional chain, is we should actually be saying, is it greater than or equal to 0? Because if it's negative, that's the problem. Oh my goodness. So do I have to go through here and do this for every single thing? Greater than or equal to 0. Is greater than or equal to 0. Oh my goodness. Yes, so that does work. Wow. Whew. Okay, I do not like that at all. Is there any better way to write this? I could say, like, 0 is... I could say -1 is less than this. No, that's not more readable at all. Okay, I guess I just literally have to go through here and do that for all of them. Luckily, I haven't encountered this problem before, or maybe not so luckily. So, okay, if we're just doing fprintf-s, so let me summarize the problem. fprintf-s attempts to print something to this output stream. If there's an error, it's going to return a negative number. Otherwise, it's going to return the number of bytes written. So, if I just do this, that's okay because I'm printing one thing to the output stream. But if I was to print an empty string, then suddenly this would return 0 because it has printed 0 characters to the output stream. And that 0 is considered false, so that's going to short circuit the rest of this conditional chain. So I think I literally have to do this. I think it actually doesn't matter for these because I can tell that they're not going to cause that problem, but I'm just going to do it to all of them because I want to be consistent. Okay, wait a minute. No, I think this should actually be... Should this be plus? I should be returning plus, right? Instead of and? Okay, but plus evaluates... the plus doesn't have the right semantics, though. So, since I'm returning an int up here, I want this display expr function to sort of behave like fprintfs. Which means that it should be returning the number of bytes written to the output stream. Oh my goodness. So what I actually should be doing is, instead of and, I should be doing plus. And we add this in and this in. But then I don't have the short-circuiting behavior of double ampersand. So I think what I actually want to be doing here is returning a Boolean. So display arglist returns a Boolean. For all of these, they should return a Boolean. Okay. Display statement, this actually returns a Boolean. Display expr. Display arglist returns a Boolean. And for all of the fprintf things, I need to be saying that needs to be greater than or equal to 0. For all of these, it doesn't matter because that's already a Boolean. Okay. Display expr. Where is... Don't I have like... Oh yeah, I have display decal. Display arglist, display decal. This should be Boolean as well. And these ought to be greater than or equal to 0. Greater than or equal to 0. And if this fails, I mean, alright. So this ought to be... I can just merge these two. Okay. It's not that big of a deal. And then down here we want pound include that. Alright. Alright. Let's continue where I was. Okay, so for all the fprintfs functions, I need to add this. Okay, this is looking good. And then for none of the display functions do I need that. fprintfs. Display function I do not need. For fprintfs, greater than or equal to 0. Display function, I don't need it. fprintfs, I do need it. fprintfs, I do need it. Same with here. Same with here. And I think that's good enough. I think we're done. Yeah, that's correct. Okay. Let's see if this compiles. Did I forget anything? We still have this error. What? I should be returning true in this case. Okay, because it's successful. All right. Yeah, we got it. All right. Our test case works. It'd also be cool to test our extra feature, which I'm stealing from Rust and any other sane language, which allows you to have trailing commas. Because I really like that feature. So let's test that out. And all right, it does not print. It doesn't remember that we have a trailing comma, but that's okay. All right. So let's commit this. Parse argument lists and function calls. Sync those changes. And what should we do next? I have some to-dos up here. Structure, union specifier, enum specifier. These are for types. I haven't really gotten to types yet. Where are we with expressions? Size of operator. We need to parse a unary expression. Okay, I can add this. I cannot. So there are two cases for parsing the size of operator. One is you could have size of followed by a unary expression, and the other is inside of parentheses you could have a type name. And this is actually pretty funny because so I've been doing this, and this is a unary expression. It's actually funny that you can't do like that. I guess you can, but you would have to have parentheses around it. But I suppose I could be doing this size of without the parentheses. But I would rather just have parentheses around this. Okay. So we need to be able to parse a unary expression or a type name. And I cannot really parse a type name yet. Actually, maybe I can. All right, so let's add size of. Let's add the size of expression type. Where do we define expressions? Here, this is a unary operator. Have we done? Yeah, unary operators down here. Expr size of expression, and let's do expr size of type. Yeah, I think that distinction is going to be important in the compiler just in general, so that's fine. I'm willing to split that there. All right, size of expression, size of type. Unary operand, unary op. So this is fine for the expression. Struct struct type pointer size of type. maybe I should duplicate this just for readability and say size of expr. So we'll have two cases here. All right. So we need to tell it how to print these out. Case expr size of expression, and case expr size of type. So for this one, we want to return fprintfs. To the out, we want size of, and an expression does not need parentheses. I do need a space here, because if the next expression, if the expression is not parenthesized, then, and it's like an identifier, then I can't merge size of in the identifier. So I do need a space here. And we need to say greater than or equal to 0. And display expression to the output stream expr as size of expression dot operand. And then down here, let's copy this. We're going to say as size of type type. And in this case, I do want parentheses around it. Okay, so we want and fprintf s to the output stream, closing parenthesis, and greater than or equal to 0. Ugh. All right. So that's how to print them. Printing is actually important beyond just being able to test it like this. And these aren't like great tests because I'm just looking at them, visually. But this is effectively the output of the compiler. So eventually, I would like to be able to just say, have a function like this, display something. It's going to be display like translation unit or file. And it should just print out the AST as into a file, and that will be the compilation step, the lowering from AST to text. So this part is actually important beyond just pretty printing for debug purposes. Okay, so where were we working? Size of, yes. Unary expression. All right, so this is, if we get an expression, then we need to say, let's set expr equal to malloc size of star expr tag equals expr size of expression. And then expr as size of expression dot operand is going to be equal to what is operand? Oh, operand is here. Yeah, that makes sense. Okay. Operand equals operand. Can I just return expr at this point? I think so. Okay, otherwise, we need to parse all three of these things. And let me just copy all of this down. Instead of this, it's going to be expr size of type, and the size of type dot type is going to equal type. So the type that we parsed, parse type name. And I believe parse type name is the top level type parser. I think. We might need to change that later. No, it says type name up here. I think I looked into this already. Okay. I'm not doing increment or decrement, so these are the plus plus, the prefix plus plus, and prefix minus minus operators. I'm also not doing a bunch of these. I'm not doing unary minus, maybe I should. I'm not doing tilde. I'm not doing unary plus. That's not very useful. Do I need unary minus anywhere? Let's ignore it for now. And this is ampersand, so that's actually, I don't like that they're calling it and, but that's for pointer referencing, or creating a pointer from a data member. So if you get an ampersand, then it's like a reference expression. Okay. So let's test out size of. If we go down here, yank and paste, paste. Size of an expression and size of, whoa, size of a type. I think it has to be a pretty simple type at this point because I can only parse very simple types. Okay, void is a keyword, so I think this should be okay. Any errors? Yes. Up here, I need a semicolon. Incompatible pointer types right here. Display expression. No, it needs to be display type. Okay, so size of expression works. Expected token open paren got token void. Interesting. Expected token open paren got token void. This is our lexer. Ah, I see. So I think what happened is a unary expression is a conditional expression, which that's not it. Conditional expression is a logical OR expression. We gotta just follow this all the way up. Logical OR expression is logical AND expression, which is an inclusive OR expression, which is an exclusive OR expression, which is AND, which is an equality expression, which is a relational expression, which is a shift expression, which is an additive expression, which is a multiplicative expression, which is a cast expression, which is a unary expression. Jeez. Huh. Where are we allowed to have parentheses? Am I wrong that a unary expression... Okay, a unary expression could be a postfix expression. Okay, where is postfix expression? We gotta follow this up. Postfix expression is a primary expression, and I believe a primary expression allows parentheses. Okay. So I think what's happening is we're going into parse primary expression. We're getting down here. We can accept an open parenthesis, and then we attempt to parse an expression. This is actually going to fail. And if this fails, I wonder if we could like print something here. Let's do we not have what's the problem? Printf. Does it just not like this? Oh dear. I think what's happening is we're attempting to parse an expression, and a type is not an expression. Unexpected token, expected, an open parenthesis, got token void. So somehow we go into parse expression, and like at some point we're needing to parse a new expression, and we're parsing a void. Where are we expecting to parse an open parenthesis? So where is lexer expect lxr comma token open paren? Ah, okay. Where is this? Oh, this is what we were just working on. So this should be accept, right? Not expect. I mean, it really should be expect. Okay, and that's the only place that was happening. Well, let's see. I don't think that's going to change anything. Test failed. No error. Okay, so that means we're returning null. Parse type name. Oh, parse type name is not implemented. What? Parse type name is not implemented? So we're not even hitting this case down here? Parse type name. But we're not... What? We are hitting this. Open paren, close paren. Type name. How come this is not getting called? Lexer accept open paren. And down here, I definitely have an open parenthesis. So let's try debugging. 801. Okay, we want to get rid of this. All right. So we just printed this. Yeah, this is the perfect spot. The Lexer input, we've actually consumed void somehow. So at this point, the Lexer has consumed void. And the current token, wait, current token is token open parenthesis. The next token is void. This is so odd. We're right here where we need to try to accept an open token. Lexer accept, though, is going to check next token tag, which is void. Okay, and that's why previously we had been saying, all right, we were expecting open parenthesis, we got void. Because when this was expect, that's what was happening. Okay. All right, let's stop. I want to add a breakpoint here. And let's run it again. So we are size of, I think we're about, no, this is, we're about to go into, okay, this is weird. What's the input? Input is empty. Okay, continue. Input is empty. Input is, I can't see that. Parenthesis star expr, close parenthesis. Okay. We're looking at the size of token. We're looking at the size of token. So this ought to work. If I step over, then yeah, we accepted the size of token. We're now looking at token open parenthesis. And we need to parse a unary expression. I believe this is going to work, so let's skip here. We're now in the case where we're trying to do size of void. Size of void. And we're here, this is in the, yes, so we accept size of, step over. Now we're going to attempt to parse a unary expression. All right, attempting to parse a unary expression. This is the order it's telling us to do it in, right? Unary expression first, and then left parenthesis, right parenthesis, huh? Okay. Parse a unary expression. So I imagine it's going to go in here. It's going to attempt it. It's going to consume a parenthesis, an open parenthesis, and then it's going to figure out that void is not a valid. Void is not a valid expression because it's a type name. So then it's going to come back out, and we're not going to reset the input back to where we were. So it's almost like I need to fork, like, this is like a backtracking point. All right, let's test that out. I want to see if I'm right. So if I were to say lexer struct lexer saved lxr equals lxr star lxr. We're going to copy that into here. We're going to just save it. Temporary. Then, if this fails, we need to restore the state. So we need to say star lxr equals saved lxr. Let's just see if... Let's see if that solves the problem. Not implemented. I think it did actually solve the problem. Alright, I do not like that. But, I mean, it's not the end of the world, I guess. Ugh. That's... Is there a way I could reorder these two so that I don't have to do this? That's really annoying. That's so obnoxious. Oh, goodness. You know what? Find a fix for this problem. Restore hack. Restore lexer state. I gotta think about that more, but let's continue. So we're calling parse type name, which is not implemented. What types do we have? Specifier qualifier list, an optional abstract declarator. Oh goodness. Abstract declarator is a optional pointer and then a direct declarator or a pointer. Oh my goodness. Type name, type def name. Oh, sorry, that's different. I'm not planning on using type def because that's a little more complicated than I'm looking for. Where are the types? Types are up here. Parse type specifier. Type specifier. So where is type specifier used? Specifier qualifier list. Anywhere else? Type specifier. This is the top level declaration specifier. Type specifier. So where is specifier qualifier list used? Right here. Okay. So we should just create a new function. Return specifier qualifier list with lexer. Alright. Specifier qualifier list. Specifier qualifier list. Paste this here. Parse specifier qualifier list. I see I need to say parse here. Parse a specifier qualifier list. Specifier qualifier list. We're going to say, for now, finish implementation. Just return a parse type specifier with lexer. So this is the functionality that I've already implemented, which parses void, character, int, and bool. So it's very simple. But I think that might be enough for this to work. Let's see. Yes. All right. So that works. Where did I put? Oh, okay, I got rid of that printf statement. Good. Okay, so we've got like a big hack in here, but that's fine. We can now parse size of. All right, so let's commit this. Parse size of operator. That was surprisingly strange. Commit. Sync changes. All right, what should we do next? Maybe I should be working on types. Maybe not. Where's the type name? Oh boy. Statements. Yeah, there's a whole bunch of statements I've not implemented. You know, I really ought to make this a macro. Unimplemented. Let's make this a macro. I don't want to support macros in the final in the self-hosted compiler, because I don't want to have to parse them. But let's do this since this is just a development thing. Unimplemented is going to be this. Ah, okay, nice. Temporary macros. Development macros. Safe to delete. Delete when bootstrapping. Okay. And we can do this here. Unimplemented. Implemented. Are there any other places I'm doing that? Printf. No, that's it. Okay. Let's commit that. Add unimplemented macro. Sync changes. Okay. Parse a statement, display statements. Statements are not implemented at all. What other expressions could we teach it how to parse? Argument list. Oh, I forgot to remove that to-do. This is a to-do, but it's actually a compound literal. So in C, you're allowed to say like, you know, x equals like my point struct my point, and then give an initialization thing in here, like thing equals 1. I don't know, like x equals 1 dot y equals 2, like that. So that is what this part of the grammar is talking about. but I'm not going to support that for now. We'll definitely want to support that at some point, but not right now. Okay. Let's continue along. Ignored, 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 but no to-dos. So this is done. Unary expression, unary operator, unary expression is done, except for the weird hack, which I need to think about more. Cast expression. All right, let's handle cast expressions. Ooh. And I think we're right back to the same problem we just had. So the problem is, if we parse a left parenthesis, and then it turns out that this is not a type name, we need to backtrack and try to parse a unary expression. So like, if the expression we're trying to parse is 1 plus 2 inside of parentheses, then it's going to accept the parenthesis. This is not a type name inside here, so it's going to break out of here, but then when we go to parse a unary expression, it's going to start on 1 instead of on the parenthesis. So how do we handle this? And why is this even a problem? It's like I need a look ahead or something. Why is this like an ambiguity in C almost? Alright, well, I guess we'll just continue using this hack. So, struct lexer saved lxr equals star lxr and star lxr. Hi.
Come on. Streaming?
Yeah.
Cool.
This is kind of a mess of a stream, but
I feel like you've been streaming for a while and going long.
an hour and a half.
Oh, that's longer than a half hour.
Yeah. I warned people. The title is like implementation stream, so. Saved LXR. Should I like put this inside of a block? Sure, why not? Alright, so we need to attempt to parse a type name inside of parentheses. So if lexer accept lxr token open parenthesis, and we need a type, struct type pointer type equals parse type name with the lexer, and lexer accept our token close paren, and finally a cast expression. So we call this recursively? Okay. Expr equals parse cast expression with the lexer. If that's the case. Oh, oops. That should be here. Yeah. And I need struct expr pointer expr. If that's the case, then we can allocate. I almost feel like this should be inside of its own scope as well. We can say we need to allocate a new expression. Oh, this is a cast expression, so I should have done this beforehand. Expr cast pointer type and an expression pointer exper. We need to teach it how to display this expression. Case exper cast return fprintf cast expression, yes, fprintf s to the outstream, open parenthesis, is greater than 0. Display type to the output stream exper as cast expression dot type fprintfs to the output stream, close parenthesis, space, and then check that that's greater than 0, and finally display the expression to the output stream exper arrow as cast expression dot expression. Okay, now we're ready to continue down here. We can say struct exper pointer cast exper equals malloc size of star cast exper. Then we say cast exper arrow tag equals exper cast expression, cast exper arrow as cast dot type equals type, and exper equals exper. And finally return the expression, the cast expression. If this fails, though, we're going to skip past all this, restore the Lexer state, and then try to parse a unary expression. Ugh. Okay. Let's write a test for this. Let's cast something to an int. Let's cast true to an int, see if that works. Too few arguments. Yes, here we need to pass the Lexer. And int true, yes, that worked. All right, cool. Parse cast expressions. Sync changes. That's what we were just doing. Let's do multiplicative expressions next, just because that's going to be interesting. Do I even have... Yeah, I do have star. I don't think I'm parsing, like, division and modulo, though. I don't really support that. I mean, you can do division and modulo if you want, but this language doesn't plan on parsing that. But I'm lexing star already, so I might as well do this. Although maybe I should just kind of skip this and do multiplicative expression, or do additive expressions. Sure, let's do that, because those I know I do have to support. So we want to define an addition expression. We want to define an addition expression. So let's go back up to our expressions. Expr add. Struct left-hand side and right-hand side. Is that what I should call it? It's not really. They're going to be expression pointers. Let's call it X and Y. Binary op. So up here I was calling this unary op, and I'm using it for all of the unary operations. The only difference in all the unary operations is the tags. So these are all the unary operations. Well, these are the 3 unary operations that use that. The only difference is the tags. So I'm going to do the same thing with binary operators. Okay, so let's define how to print them. Case expr add return display expression to the output stream expr as binary operation dot x, and then fprintf s to the output stream space plus space is greater than 0 to check for errors, and then we want to display y. Okay. So then down here, now this is interesting because we do have to take into account the star. So let's start. First thing we want to do, let's get struct expr pointer. Let's get an accumulator pointer. So this is going to sort of keep track of the tree of expressions. And is this going to be the most recent expression? Or is this going to be the bottom and we're going to keep adding to it? I don't know. Let's figure it out as we go. So first thing we're going to do is we're going to say if the accumulator can parse a multiplicative expression. Or I suppose we should say if it can't, we need to return null immediately. Otherwise, we have set accum, the accumulator. Next, we're going to go into a while loop. Lexer except LXR token plus. Am I not even tokenizing plus? Oh wow. Okay. Let's quickly add that. Where's my list of tokens? Symbols token plus, and we need to do this down here. Token plus, and we need to do it down here as well. And it's important that it comes plus. it's important that it comes after plus plus, because we need to lex or tokenize the plus plus as its own thing, and then the plus as its own thing. Okay. Token plus. Token plus, yeah, so it is accepted. While we keep accepting a plus, if we can accept a plus, oh, and I guess at the very end we should return the accumulator. However, at this point we need to parse another multiplicative expression. Okay, so it's going to be kind of the same thing here, except we need a new pointer, expr pointer, new expr. If you can't parse into new expr, parse multiplicative expression with the lexer. Then again, you need to return null, and honestly, like, throw an error. So maybe we should even be saying error unused expression, expected expression after plus got nothing, something like this. Exit status 1. Okay, so we parsed a multiplicative expression. Now what do we do with it? We need to maybe this should be called like y. And then we need another expression pointer called new expression, where we will allocate size of star new expr. New expr arrow tag is going to be equal to, because we're doing plus here, if we also parse minus, it's going to be a little more complicated, but for now we're only doing plus, so this is going to be expr add new expression as binary op. X is going to be the previous accumulator, and Y is going to be Y. Okay, and then set the accumulator equal to the new expression. All right. And if you can't parse a plus up here, then we'll just skip the while loop and return the accumulator, and we've already parsed a multiplicative expression, so that's okay. All right, let's test this out. I'm doing this completely kind of opposite to the way that I should be doing it. I should be writing a test first, right? All right, so let's add a test case where we say 1 plus 2. One plus 2. All right, let's try plus 3. 1 plus 2 plus 3. because I'm not convinced it's doing it in the right order. I'm still a little concerned about that. 1 plus 2 plus 3. All right, I mean, it's looking good. Should I be worried about the whether it's grouping them like this and then like, you know, should I be worried about the associativity? I think that's built into the grammar. So hopefully we're okay. Okay, let's leave it at that then. Am I using subtraction anywhere? I think I'm actually using subtraction somewhere. Yeah, I'm using subtraction right here, unfortunately. So I do need to implement subtraction. I think I'm going to stop here, though. I think I'm going to stop the stream. We're at like almost 2 hours, I believe. Yeah. So let's call it quits for now. We've made a lot of progress, and I can continue working on this on my own, and getting the boring parts out of the way. Maybe next time we'll be working on statements. I'm not sure. We'll see. Okay, so let's commit this. Implement implement parsing for plus expressions. Okay, commit. Sync changes. And I'd like to, at this point, go back to the repository. We just did this commit. I'd like to go browse files, copy this, whatever it's called, and then we're going to say repo at end of video and paste that one in there. So I'm trying to add these two links to the video descriptions from now on, where it will say where we start and where we end, so you can look at the code at the beginning and the end of each video. Okay, so let's save those changes, and I'm going to shut down the stream at this point. So that's it. I don't think anyone's watching, but if you are, have a great day. Bye.